Eric Burgess here. The average number of chocolates consumed per month by a person is 29. A random sample of 15 people gave the following. Then we're given some data here. So we're going to need to use this data to find, the mean, standard deviation, all those kinds of things for this sample of people. Given the distribution is normal at the alpha equals 0.05 level of significance, can it be concluded that the average is different? Assume the population standard deviation sigma is 2.61. So it's important they tell us the distribution is normal because our sample size is less than 30. So this means that we can go ahead and use a z-test because we have the population standard deviation and we know our distribution is normal. So our first order of business here is going to be identifying the null hypothesis and the alternative as well as the claim. So let's do that. So the null hypothesis, H naught, involves, we're talking about averages here, right? The average number. So this is going to be a mean. So population mean is going to be equal to 29 because it says right here, the average number of chocolates consumed per month by a person is 29. It's not connected to a sample of any kind. They're just making this statement. Now, the alternative, HA, some people call it H1, whatever your instructor uses, is that the mean, right? If we come down here, we want to see, can it be concluded that the average is different? So we're just saying that it's not 29. It's something else. So we say, nope, not 29. This tells us that it's a two-tail test because it's got a not equals to. That lets you know it's two-tail, and we should identify the claim. So the claim is what we're trying to conclude, and it says right here, can it be concluded the average is different? That means the alternative is also the claim. Good to point this out here. All right, next order of business, we need to get the numbers out of this thing. Now we've already been given a couple of them. For example, we know that the population mean is given to be 29, and we know the population standard deviation is given to be 2.61. But what we don't know is the sample stuff. So we still need an X bar. What is that? And we also need a sample standard deviation. You could compute this by hand, but that's like just super not worth the effort. Just go ahead and use a calculator to do it. So I'm going to go to stat. Then I'm going to go to edit to go into a list. If you've got stuff in a list, just go ahead and clear it out by going up and pushing clear and then going down. It'll clear the list for you. We're going to go ahead and we're going to put these in. So we got 25, 32, 35, 25, 30, 26, 25, 29, 32, 30, 27, 28, 27, 30, and 34. And you see we're on item number 15. So that's one way to tell also where you're at in the list. Okay, so the most common mistake I see by a long shot is misentering something on this step. So always go back and double check. So we got 34, 30, 27, 28, 27, 30. Okay, that's the whole bottom row. 32, 29, 25, 26, 30, 25, 35, 32, 25. Beautiful. This is our data. So now we're going to come into stat again. We're going to go to calculate this time. We're going to go for one var stats. This will give us a sample mean and a sample standard deviation for these numbers. So we're going to go ahead and do that. Make sure the list you used is the list that's listed here. So list 1 is the list that we put all these numbers in. We don't have a frequency list, so we need to clear this so that it has nothing. And then we're going to hit calculate. It's going to give us a sample mean. Whoa, look at that. It matches the population mean. Well, this is looking pretty amazingly accurate. It looks like the null hypothesis has some clout here. So we've got a sample mean of 29. So let's go ahead and put that in. And a sample standard deviation of 3.25. That's the SX right here. We want this one because it's a sample. All right, great. So having this, let's go ahead and get our test stat. Some people draw a picture first. I'm going to go ahead and do the test stat. So for the test stat, you need a formula for this thing, or you could use a calculator. We'll go over both ways. Or you could use a p-value. There's a lot of options here. So let's do the formula first. So the formula is a z-test. So we're going to do z is equal to, and you could look this up if you don't remember it, but it's the mean, population mean minus the sample mean, or my mistake, sample mean first. Sample mean minus the population mean, all over sigma divided by the square root of n. Now, actually, I don't think we actually needed this. That's just bonus, just a big bonus right there. So we're going to get, when we do this, we're going to get 29 minus 29 over sigma, which is 2.61, divided by the square root of n, which is n is 15. So total number of numbers, right? That's what it is, the number of samples. So our sample was of 15 people, and we have 15 numbers. So this is going to be 15. So doing this, we could plug this in the calculator. We will get out a test stat. Let's go ahead and find this out. So we're going to go to stat. We're going to go, or not to stat, we're just going to enter this in the calculator. So we're going to go to the front, and we're just going to put in a fraction here and do 29 minus 29, that's 0. 0 divided by anything is going to be 0. So our answer will be 0. But just to appease people, I'm going to go ahead and just type in the bottom as well. 2.61 over square root of 15. And this would be 29 minus 29 if you wanted to type it all in. But this would give us 0, right? So we get 0. So our z-score is 0. Now, another way you could get this z-score is you could go to stat, and after you put all the numbers in the list, you could go to calculate and then tests. And then on number 1, there's a z-test. And you're going to go ahead and choose data instead of stats, because this time we were given a bunch of data up here. So we're going to go ahead and choose data. It's going to ask for the H naught, which would be, or the mu naught, the population mean, which would be 29. And our sigma is 2.61, as we were given here. We also wrote it down here, 2.61. And it's going to ask for the list instead, because it's going to find this other stuff it needs, specifically the sample mean and the number of samples from our list. So we put that in list 1, so that's fine. Frequency is 1. You're going to want to leave this at 1. If you didn't use a frequency list, just go ahead and leave it at 1. And then we're going to say, okay, our alternative hypothesis that's not equals, this means it's two-tailed, we're going to hit calculate. It calculates it for us, and we get a z of 0, so we got the exact same thing. We're given a p-value here as well. P is equal to 0.9999. And so you could use this to draw our conclusion already, actually, if we want to. And that's that. All this other stuff we don't really need. So let's go ahead, let's draw our picture, and let's find what this thing looks like. So we're going to go ahead, we're going to draw our graph. Something like that, right? It's approximately normal. Here's 0. Remember, the standard deviation is going to be equal to 1 for a z-score, and the mean is going to be equal to 0 for a z-score. This is going to be important when we look up the level of significance if you use the calculator to do it. So, okay, now we're going to go ahead and find our level of significance, our critical values. And this is given by an alpha of 0.05. So that means 5%, but half of that 5% is down here because it's a two-tailed test, and half of it is up here. So it's 0.05, 5% total, but it's divided by 2 because half of it's right here, and half of the 0.05 is right here. So if we do this division, and we do 0.05 divided by 2, we get 0.025. So this is an area of 0.025. It's an area of 0.025. Whoops, wrote that kind of weird. 0.025. So since we know this curve is symmetric, if we find the lower one, it'll be negative, and then we can just make it positive to get the upper one. So to find this, you could use the calculator or the chart. I'm going to use the calculator first, then we'll look it up in the chart. So we're going to go to, this is related to the normal distribution, right? So we're going to go to the distribution menu in the calculator. We're going to hit second, distribution. Then we're going to go down to inverse normal. So because normally, right, we give it a z-score and it will give us an area, but we want to go backwards. So that's like an inverse. So we're going to do an inverse of the normal. It's going to ask for area. I've already got it entered in here because I've done a couple problems that had the same level of significance. So you put in your area of 0.025, so because it's two-tailed. And then again, because it's a standard normal distribution, we're using z-scores, the mean will be 0 and the standard deviation will be 1. So do not mess this up. I see this is another common mistake. People will put in the stuff from their problem where you're looking at a pure standard normal distribution. So don't use the ones you have from the problem. Use just the ones that you know are there by default. This is a z-score. So we're going to hit paste, enter, and we get out the negative version because we looked up 0.025, and this returns the area to the left. So it's this area shaded. So we're going to get, for this, I'm going to erase this here a bit. I'll do it in green. Our critical value is negative 1.96. This is the critical value. That means on the positive side, we're also going to have 1.96. Great. So that's what we have there. Now, something to be aware of is we've split ours in half. So our alpha is given to be, right, it's 0.025 is the alpha. Is this alpha. And this alpha is also 0.025. But this p-value up here, if you use the p-value method, is both the alphas added together. So you would compare this p-value to the original p-value of alpha equals 0.05. Now, obviously, this p-value is tremendously bigger than this alpha, so we would fail to reject the null hypothesis, and that would be the decision if you use the p-value method. Let's keep going and use our test stat instead. So if we were to plot our test stat, I'll do it here in purple. It would go right here, right? There'd be a 0. This is where the test stat is, test stat. And it lands smack dab in the middle. Well, guess what? This, when it lands in the middle, we're not in the shaded region, so we'd fail to reject the null hypothesis. We think the null hypothesis is right. Some professors just say, do not reject the null hypothesis. We were trying to conclude something else, so we've failed to reject it. It's not, this point isn't that important, but you might run into a professor who cares about this detail, so just be aware of that. Now, I said I'd show you how to get this number also using the chart. So we know that this is an area of 0.025. So if we just look this up in the chart, let me see where my chart's at. Here it is. And we look up in this chart for 0.025, which would be, let's see here. Remember, we want to look in the middle because it's an area. It's not a z-score. We're trying to find the z-score by knowing the area. So 0.025. If it's not on here exactly, you look for the nearest number, but this one is on here exactly, so that kind of works out. Look at this. Negative 1.96. Oops, I'm covering it. Oh my goodness. So we see we got 0.025. We got negative 1.9 and then 6. So you see we get the exact same thing, negative 1.96. If it's off by like one number at the very end, that's okay. Because sometimes it's not directly on the chart, so you have to approximate. But you see we get the exact same z-score, or critical value, I mean. And this critical value is symmetric, so we can just plop the positive one on the other side. So since our test stat didn't land in the shaded region, we say that we do not reject, or we fail to reject, the null hypothesis. Because this means that the null hypothesis was right, or at least, not that it was right, but we think it's right. We think it's correct. We have evidence to support the fact that this null hypothesis appears to be right. Based on the study that we did with all these different people and our data, it supports the notion that the mean is indeed 29. Now, we still need to say something about the claim, though. So if we look up here and we said the claim was the alternative, so we don't think the alternative is correct, right? Because we think that the null hypothesis, we think this is true, so we don't think this is right. Now, in order to prove that this is wrong, we would need everyone's data on how much chocolate they eat. But we only have 15 people's worth of data. So at best, we have evidence that this is wrong. So we would say there is evidence to reject the alternative. Or you could say to not support. But the point is that we're not claiming that it's just straight up wrong. We just have evidence that it's not correct. If we were like on a trial or something, we would say, yeah, we don't think this is right. We don't think that the alternative is right based on the evidence presented. So that's what we would say. And then you could go on and say here, there's evidence to reject the alternative hypothesis that the average number of chocolates eaten by a person in a month is different than 29. You could write all that out here just to show that you understand the conclusion that you're drawing. Because just making this conclusion, sometimes you need to be a little more specific. So I'll leave that up to you to write out the rest of all that stuff I just said. But you just want to tie it back to the problem because it's just a little more helpful. If someone just wants to read the end, like what was the conclusion, then that's what you would do. So this is the process for doing a question like this. And that's how you deal with a problem that gives you data instead of the statistics directly. You just compute them as you go and find what you need from the numbers. And then it's all the same stuff. You get your test stat using whatever method you like, plot it on a graph, compare it to the critical value, the shaded region. You could use the test stat value method, or you could use the p-value method. And then you just draw your conclusion at the end. And that's all you got to do. If you have any questions about this, feel free to let me know. Subscribe and hit that bell icon for future videos. And we'll catch you in the next problem.